Fantastic. Hello, everyone. Welcome to the 120th online Spintronics seminar. It is my great pleasure to introduce our speaker today. Dr. Katrin Schultheiß received her PhD in physics from the TU Kaiserslautern, Germany in 2013 on spin wave transport in two-dimensional microstructures. Since 2015, she works at the Institute of Ion Beam Physics and Materials Research at the Helmholtz-Zentrum Dresden-Rossendorf in Dresden, Germany. As a member of the Department of Magnetism, her research is focused on the study of linear and nonlinear magnetization dynamics in micro and nanostructure, as well as in spin textures using Brilliant light scattering microscopy. So without further ado, Katrin, please take it from here.
Thank you very much for the kind introduction, and welcome everybody here in Germany or in Europe to this late hour, or in the US or wherever you are right now. It's a pleasure showing some of our results, which will be mostly dealing with self-induced Floquet magnon states. But before I get actually started, I would like to thank all the people involved in this project, most importantly, two PhD students, Christopher Heinz and Lukas Körber. Christopher did most of the experimental work, and Lukas was pretty much working on micromagnetic simulations that I'll be showing in this talk. And then, of course, we have the entire team at HZDR. We have nanofabrication facilities also at HZDR. And then we have external collaborators, Jovo Kim and Thibaut de Volta at the Université Paris-Saclay, mostly doing simulations in this work, but also experimental results. And then Johan Menting at Radboud University, he's working on the theoretical background for us. So Lukas actually finished his PhD very recently, and he's so focused and interested in hardcore theory that he actually enjoyed not doing simulations anymore, and he wants to work with Johan now on theory. So he's moved to Nijmegen now to work there. Okay, so my talk will cover the following topics. So first of all, I'll give a very general introduction into a magnetic vortex. Then talk about the gyrotropic motion of the vortex core. Then I'll explain you what magnons live inside magnetic disks and how they look like, what dispersions they have and such. And then I'll show you how we can use this nonlinear action between different magnons living in a disk to do pattern recognition. And last but not least, I will then explain what the Floquet magnons are in this system. Okay, so let's get started. One of the very first experiments done on magnetic disks was actually by Coburn and co-workers, where they wanted to look at what dimensions yield a single domain state. So they fabricated different micromagnetic microstructured disks. In this case here, I show an example of 300 nanometer diameter and one with 100 nanometer diameter. And then they measured the hysteresis loop in this, and then they saw that they behave differently. So the very small structures behave like a single domain, which is shown down here. And the larger structures, they have a different characteristic hysteresis, which they then relate to the formation of a vortex in this structure. And to my knowledge, that was the first results that actually show what the magnetic vortex looks like, or this flux closure state looks like in micromagnetic simulations. So this is a picture from their paper. And you can see that they have all the arrows showing what the magnetization configuration is in the system. And with this, we already come to one of the first most important characteristics of a magnetic disk, which is the vortex circularity. So depending on what orientation you have of this in-plane curl, you can either have a clockwise circularity or a counterclockwise circularity, and then associate these certain numbers with this. And this circularity determines how this magnetic texture reacts to static in-plane magnetic fields. So here, I show you for an in-plane magnetic field pointing towards you, and depending on the circularity, you have a different distortion of this magnetic texture. Because of the Zeeman energy, of course, the magnetic domain that is parallel to this external field increases, and the domains which are antiparallel decrease, so that you actually have a displacement of your texture perpendicular to the direction of your external field. But then, of course, we have another thing inside these magnetic disks, which is the vortex core. And the polarity of this was measured the first time by the group of Teruno. And they did MFM on 1 micrometer wide permalloy disks, as you can see here on the right. And they see in the very center either bright or dark contrast, depending on whether this core polarity is turning out of the plane or into the plane. So these are the other two numbers you can get in a magnetic vortex. And if you combine these with the circularity, then you end up with 4 stable ground states. And the circularity times the polarity gives you then finally the chirality, which can be either positive or negative in our system. And these characteristics determine how the magnetic vortex reacts to changing magnetic fields. As I already said, a static external field displaces the vortex, and this displacement is only determined by the circularity. So if you look at the dynamics of the core, the starting point is governed by the circularity. But if you then remove the external field, of course, the vortex core does not go straight back to its equilibrium position, but it starts to gyrate. And the orientation of this gyration is only determined by the polarity of the core. So if it's clockwise or anti-clockwise, it's only determined by the polarity and does not depend in any way on the circularity. Okay, these vortex resonances of the gyroscopic motion of the vortex core have also been studied a long time ago by the group of Sam Bader at Argonne, where they looked at how does the frequency of this gyrotropic motion change with the dot aspect ratio. And they found out that the larger and thinner you make your magnetic disk, the lower the gyrotropic motion resonance frequency, and the thicker and smaller you make it, the larger the frequency. But typically we look at ranges of a few 10 to 100 megahertz in systems that we look, which is pretty much, it's permalloy most of the time. So far, so good. So if you're interested in learning more about magnetic vortices and getting all the details, I recommend a chapter in this nice book on topology and magnetism. I put the link here if you're interested in having a closer look at these structures. But so far we looked on the gyration of the vortex core and how the texture changes when you apply magnetic fields. But of course, we can also have long-range excitations in the system, which are the spin waves, right? As we probably all know, a spin wave is a collective excitation of all the magnetic moments. And then if you have neighboring spins, they have a slight phase shift in between them. And then this propagates through a magnetic system like a wave. They can have frequencies in the gigahertz to terahertz range and wavelengths ranging from micrometer to nanometer. And which is most importantly for this talk, they are highly nonlinear because spin waves mediate the medium they live in, so they interact very easily with each other. And if you look at a magnetic disk, of course, because of quantization in radial and azimuthal direction, you get standing waves. Here, I plot one of them in a video where you show there is no quantization in the radial direction, but quantization in azimuthal direction. And then you have neighboring nodes always precessing out of phase. This is, of course, not the only one. We have many different modes in this system, and we can distinguish them, as I already mentioned, by their radial mode number and their azimuthal mode number. And if you look at the details of the dispersion, you see that for increasing azimuthal mode number, the frequency decreases, and for increasing radial mode number, it increases. And this is very reminiscent of the character of backward volume in Damon-Eschbach spin waves. If you look at spin waves that are propagating in the azimuthal direction, they propagate parallel to the magnetization direction. So they should have a backward volume character with decreasing energy if you increase the k vector, which is the case here. But then in radial direction, you have a perpendicular propagation with respect to the magnetization direction. So increasing energies, just like Damon-Eschbach spin waves in thin films. These dispersion relations we can also calculate with MUMAX. So what we did in this simulation is we just looked at the thermal population of a magnetic disk, who in this case had 5 micrometer in diameter, 50 nanometer thickness, made out of permalloy. And you just let the system evolve and let all the modes populate just because of the thermal fluctuations. And then you look at the spectrum and deconvolute it and look at only the relative azimuthal mode numbers. So you project all your modes on a given azimuthal mode number, and you just detect, or you extract all the frequencies of these modes, which are plotted then as a radial mode number here. So the system itself is very, very well understood, and we want to look at now what's happening if we really excite these systems. So how do we measure? Typically, we pattern, as I said, a few micrometer in diameter disks, and then around this, we pattern an omega-shaped loop antenna here, where we just put a microwave current through, and then the Ørsted field, which is in this case out of plane, then excites magnetization, and we can measure this. And in our case, we use the technique of Brillon light scattering microscopy. The technique is quite simple. So we use a monochromatic laser. We focus it onto our sample with a high numerical aperture, and then collect all the inelastically scattered light and analyze this in a high resolution interferometer. And the intensity of the frequency shifted scattered light is directly proportional to the frequency of the spin wave in a given position. With our objective, we realize spatial resolution of about 300 nanometer. And a typical experiment that we do is we now change the excitation to this omega loop antenna. And for each of these excitation frequencies, we measure an entire BLS spectrum, meaning we detect at what frequencies we get any response in the system. So on the x-axis down here, you see excitation frequency, and this here is the magnon frequency, which directly corresponds to the BLS frequency that we measure. And if we do this at low excitation power, we get a nice linear response. So if we put in 4 gigahertz, we get a signal at 4 gigahertz and so on. But then, of course, because we only excite efficiently if we hit one of the modes, you see that there are maxima along this diagonal line. And if we map them in 2D, we can look at the mode structure and see that these are only radial modes, which is clear because of the homogeneous excitation field of the antenna. We are only coupling to radial modes and not to the azimuthal modes. So this is all very well understood, but the exciting stuff is now happening if you crank up the power of your excitation. So we increase this now and do the same experiment. Again, we sweep the excitation frequency that we apply to the microwave antenna and measure all spin waves that are excited in the system. Again, we get the direct response, which is the diagonal line here. But then you see that there are many, many more signals popping up, especially down here in the lower frequency range. And they appear because of a principle that's a 3-magnon splitting. So what's happening there is you excite one mode, and then that splits in 2 other modes. And of course, you need to fulfill energy and momentum conservation. So if you excite at a given frequency, the frequencies of these split modes need to add up to the initial frequency. And also, the azimuthal mode numbers need to add up to the initial mode number. And since we only excite radial modes, we always excite pairs of split modes that have the same azimuthal mode number, but with opposite sign. So we have one case where we have radial mode number 1 and plus 12, and the other one would be 0 and minus 12, and vice versa. Okay, so we end up having standing waves in our system because these are degenerate in their frequency. And the nice thing now is that this is a highly nonlinear process. So if you continuously change the excitation power of your drive, which is the black dots here, you see that if you map the intensity of all these 3 modes, that the direct response is a linear feedback, but the split modes only appear above a very abrupt threshold. Only if you cross that, you actually get this 3-magnon splitting. Okay, so this is what has made us hope for that we can use it for something very cool, like artificial neural networks that everybody talks about with the activation function of a neuron, and we thought we could use this, maybe. And that's what we tried. So we thought, okay, this threshold character could be good for pattern recognition schemes. And our initial idea was that we wanted to see if we can determine differences in microwave frequency inputs, where we have two frequencies, just in pulsed form. And what we wanted to see if we can determine the pulse order of all these inputs. So if you look at the time-integrated spectra of these two inputs, for example, they are the same. You just have two frequency components, and you cannot distinguish if you had an A-B-B-A order or if you had an A-B-A-B order. So we wanted to use this nonlinearity and take control of this nonlinearity to tackle a task like this. And the first step we took was we thought about if we can somehow prematurely drive this nonlinear process. So as I said, you have an intrinsic threshold. Only if you cross with your excitation power this threshold, then you can actually have this three-magnon splitting. But what if we can populate one of these split modes? Can we start it earlier? And that's the idea what we wanted to test. However, feeding energy into the split mode is not that straightforward because it has these high azimutral mode numbers, so we cannot couple easily with an antenna to it. Okay. So we thought we take a different approach. We patterned a sample where we have a disk. It's again 5 micrometer diameter, made out of nickel iron, 50 nanometer thick. And we have an antenna, just like before, where we can directly excite the disk. And then next to the disk, we have a conventional nickel iron waveguide and with a separate antenna. So the idea was now we couple this F+ signal of one of the split modes into the waveguide, have it propagate along the waveguide, and then via dipolar coupling, we populate the F+ mode in this disk. Okay, and that's what we tested. And it's pretty much 3 simple experiments, step by step. So first, we excite only the disk. So we feed in only the omega antenna here signal at one of the resonances in the system. It's a radial mode here. And we do this at powers that are below the threshold for nonlinearity, meaning we only get the direct response, but no split modes in the lower frequency range. Then, next step, we wanted to see if we can couple spin waves that are propagating in the waveguide into the disk. So we did a second measurement. We turn off any excitation in the disk. Only the waveguide is now excited. And again, we sweep the frequency there. And we have one resonance here that's actually propagating along the waveguide. And if we measure inside the disk, we pick up a signal. This is this F+ peak. This is measured in the disk, not in the waveguide. So this is important. So this means the dipolar fields are strong enough to couple actually to the disk and the mode in the disk. And then if we now combine the both, we see that we don't have just the F+ signal, but instantaneously get the F-. So this means we prematurely start this nonlinear process, even though it would not start at this powers on its own. So this was the first step for us to take active control of this nonlinearity and use it for something later on. However, to be honest, having this waveguide here and having propagation, as you might think, in backward volume, because we cannot apply any fields, it's not that easy. Spin waves don't like to propagate along this waveguide. So we were thinking, can we have this stimulation inside a single disk? And for that, we need to look at, again, the process of this stimulation of the other mode. As I said, we wanted to feed energy into one of the split modes. Okay? Theoretically, there is not just this one splitting channel, but many more that would be possible and would fulfill energy momentum conservation, but just their threshold is a little bit higher, so they don't start. Once one scattering channel starts, it sucks up all the energy from the drive mode, and all the others do not start, okay? However, we have many other channels in there. So if we look at the disk, If you remember, there are many, many, many modes. We can drive different radial modes, which are here now FA and FB, and they have different scattering channels. And some of these channels may be very similar, but not quite the same. Okay, so we have one active channel that goes into this, and one active channel that goes into this and this down here. There are, you have to keep in mind, other channels that may be possible, but are not populated spontaneously. However, if we now do the following experiment, we have a temporal overlap between these two signals. What happens now if we have FA first, we populate the channels that are spontaneously populated by 3 magnon splitting from FA, which is essentially the same as here. Now, since FA was already there, and then FB is coming, FB already has a different mode that it can scatter in because it's already populated. So this would be this one up here. And then the partner for this one is down here. So we hoped to stimulate different channels. If we reverse the order, things are different. FB is first, so it populates his famous channels, favorite channels, and then forces FA to scatter into other channels. And this is what we tested in experiments. So we now do time-resolved Brilliant light scattering microscopy. So on the x-axis now time, and we do pulsed experiments. So we have one excitation frequency FA and the other FB. If we do them separately, we have these spontaneous 3 magnon channels. If we now do the next step and have the temporal overlap, you see that depending whether we have AB or BA, we get totally different signals in this nonlinear response. So AB first means we have a signal down here that's not seen before. Sorry, having BA gives us a signal up here, which was not there before. And just by looking at the time-integrated spectra now, you see that there are signals popping up which really tell you the temporal order of your input. So this is essentially the main idea of this pattern recognition using nonlinear scattering in a magnetic vortex. Most importantly, it's nonlinear, hence getting the signals AB or BA is totally different from just the linear superposition, and AB and BA are also different. So that lets you determine the different temporal order of the input. Of course, having just the 2 pulses, it's very simple. Then we went one step further and tried to look at 4-digit symbols. So this is ABAB. Again, you see the cross-stimulated signal here, which is slightly different from just the linearly composed ABAB. If you do this for all 16 combinations, you get all different spectra. And I just plot a few here. We did this systematically using micromagnetic simulations, so with the MUMAX3 code. So we defined a mesh, we looked at our spectral density, chunked this up into different bins, and then analyzed the intensity in the different bins, and then did a learning process with a linear regression, and looked at what's the accuracy. So Jovan ran a lot of simulations, actually, 200. He used 160 for each combination of the AB inputs, and used 40 for testing. And then you can plot this confusion matrix. So you have your input pattern here, and then your output pattern here. And depending on the number, it tells you how well you recognize the actual input of or if you recognize it correctly, let's say. Since we have a test set of 40, 40 would be 100% recognition, which is only the case for this BBB input. And almost for the AAA input, but one is in the wrong. Anyway, we can do this learning with the directly excited modes, which are at the high frequency edge. And you see that the accuracy is not so good, actually. It's only 47.7%. If you now do the same thing and only take the nonlinear response, which is this cross-stimulated scattering of these magnon channels, then you get much higher accuracy. So means even for these 4-digit inputs, you get very high accuracy in the recognition rate of the temporal input patterns. Of course, we tested this also for the frequency combinations. different bin sizes, different or fluctuations of the excitation fields. Still, for all scenario, we get quite decent recognition rates in our system. If you're interested in all the details, I refer you to this publication down here. So this made us actually quite happy, but looking at this simple pattern, we were thinking, okay, this is nice, but having this A-B, we wanted to move on, right? We wanted to have more arbitrary inputs, do like something like vowel recognition, but that's difficult in the high gigahertz range. So we wanted to see if there is a means to actually control our magnetic vortex with signals that are lower in frequency. And of course, that lets you think of the gyrotropic motion. And coming back to that, so this is a slide I've shown before. We've talked a lot about this 3 magnon splitting now, but if you look at these modes here, I told you that we always have pairs that are generated. We always have plus, minus, 12, so meaning we always have azimuthal modes that are the same, but propagating opposite direction. We wanted to see if there's a way how to control this and lift the degeneracy of these modes. And of course, if you think about lifting degeneracy in the magnetic vortex, you stumble across, again, quite old work here by Park and Kroll, where they looked at the gyro mode and spin wave interaction. So what they did is, again, they have a permaloid disk, they measure Kerr on this disk off center, and just measure the time trace of the Kerr, and then you see they have a very slow oscillation here, and then also fast oscillation. Okay, then they did the fast Fourier transform on this and looked at the spectra and repeated this for different diameter of their magnetic disk. And what they saw is now that the larger you make the disk, the more this one peak here separates in 2. Okay, so for the 5 micron disk, they have 1 frequency response. For the 3, you could say it's still 1, almost getting 2. For the 700 nanometer disk, you clearly have 2 peaks. So what's happening there? Well, first of all, because they have their micromagnetic disk on top of a stripline antenna, they now don't couple to radial modes, but they have an in-plane field excitation, so they couple to the first azimuthal modes. Okay, so that's different from our experiment already. And then they saw that if you have the small disk, of course, you always excite plus m and minus m, but because of the vortex core, you get a lifting of the degeneracy, right? One of the modes is favorable because it has the same, the opposite circulation as the vortex core itself, and the other one has the other. So that's why they lift in energy here. And that's what we wanted to try to do. So looking at these modes, the simple idea was, what if we drive the gyroscopic motion at the same time as we drive these high order spin waves? Can we get the lifting of this degeneracy? And Lukas Körber did simulations on this, and he got this. Okay, so this is the spectrum. He drives the 6 gigahertz mode, or 6.1, and at the same time, the gyration frequency at about 900 megahertz. He does not get just 1 peak here, which we would have expected because there's no degenerate mode here. And he gets more than just 2 modes here, right? There's a whole zoo. So he gets a very nice frequency comp in the system. This was simulation. And a few years later, Christopher did the experiment on this, and we see the same thing. So this is, again, the same kind of experiment. We sweep the frequency of our microwave excitation and look at what's the response in the magnetic system. And we always plot the BLS spectra on the y-axis. The only difference now is to the previous measurements, we now have a smaller disk. It's 2 micrometer in diameter, and it's sitting on top of a stripline antenna. So same as the Park and Kroll experiment. And you can see that over quite a wide range, we get very nice frequency comps, even up here in this frequency, with very regular spacing. And the spacing nicely matches the gyrotropic motion that we would expect in a disk of this size, made from permanent. So we wanted to try to understand this and did more micromagnetic simulations. So Christopher started driving this high frequency mode and looked at what's the core doing. And initially the core is not doing much, but then after a while it reaches a steady state. And then when it reaches the steady state, all these other modes pop up. And if we then look at the movies of these modes, you see that one side of the branches always rotate in one direction. The lower side of the branches always rotate in the other direction, meaning they all have positive M and they all have negative M. And of course, we tried to explain this. The very simple approach was we have again 3 magnon scattering, but this time we don't have only like high frequency spin wave modes. We also have the gyrotropic motion that's involved in our scattering. And for that, we look, for example, at the drive frequency, which is 4.8 gigahertz. Of course, we have to fulfill energy and momentum conservation. So if we cross a certain threshold of the excitation, we can actually drive a 3 magnon splitting where we have one mode that's lower in frequency and the other is the gyro mode. And then the next order process can happen where this one then decays and you also get this gyro mode, okay? So this is how you go down the ladder of the frequency comp. The other side of the frequency comp climbing up is 3 magnon confluence. So you have 2 magnons that combine and give you one other magnon. And since from the splitting you already have the gyroscopic motion, you now go up the ladder. So you always increase your M by 1 and you always increase your frequency by 0.2 gigahertz, which is the resonance in our system. So you always end up having higher twos of this frequency comp. So that made us quite happy. And we thought we understood what's going on. But then we went back and looked at the dispersion relation of our spin waves mode. And that's what plotted here. So the white lines and the red data, that's again the simulation that you saw before of all these nice radial and azimuthal modes. And these blue data here, they are the modes that we measure in the frequency comp. And if you look closely, here's one mode that we can drive, and maybe this off resonantly, but all the other modes, they just don't exist inside the disk. So the new modes don't fit the dispersion. So we did not understand at all how we can populate them and what these modes would be. And so we were totally puzzled for a while. Luckily, we had Orion Marchand, the distinguished IEEE distinguished lecturer, visit us in 2020. And he looked at this and he said, yeah, probably this is Floquet physics. And at that time, we were not really familiar with Floquet, so we had to dig into it. So the idea behind is actually very simple. If you know Bloch, you understand Floquet, okay? Bloch tells you if you have a certain dispersion and then you have a periodic crystal, you have this dispersion many, many times, and then you can fold it over into one zone in the Bernoulli zone, and then you end up with having the bands, okay? This is straightforward. I think everybody knows this. Floquet pretty much is the same. Instead of having the periodic potential, you have now a periodic drive of your equilibrium state. And then you don't have the shift of your dispersion in reciprocal space, but you have a shift in energy. And the shift in energy is given by your driving frequency, okay? So you just stack them on top of each other, all the dispersions. Now, in our case, things are a little bit more complicated because we also have a spatial modulation. We don't just shift in energy, but we also shift in M. Okay, so we have going from mon mode, we shift up in the frequency and to the left given by the polarity of your core. And in the other direction, it's the same. You just reduce both, okay? And if you then plot the modes inside the frequency comp on your new dispersion, which we calculated now such that we do the same thing. We have just thermal noise in the MUMAC simulation, and then at the same time drive our system with the gyroscopic motion, frequency of the gyroscopic motion, and then we deconvolute all the states with the azimuthal mode that we have. And then you see all the different frequencies and just plot them. And you can now see that all these modes that we measure in the frequency comb, they actually nicely fit two modes that are in our dispersion, in our Floquet magnon bands. But if you look at the details also, you see that just shifting the dispersion is not really the simple thing. So you, in this, especially in the low M range, low azimuthal mode number range, you have a whole lot more going on. So you have a total renormalization of your entire magnon dispersion in your system. Okay, so this is what we now understood more. We wanted to see how this evolves in time. And for that, we do, again, another micromagnetic simulation. We, again, look at the thermal background in our magnetic disk. And at a certain point in time, we start the drive of the gyroscopic motion. And we look at the radius of this gyrotropic motion and plot this as a function of time. So here, time 0, we switch on this drive, and then it evolves with time. We do this with two different dampings, mainly because if you look at now chunks in time, it's easier to see the actual spectra if you have a smaller damping, because then your line width is reduced. Otherwise, everything would be blurred. And this is how the spectra looked like if you now look at different time steps here. At the beginning, before we have the drive, we only have the regular magnon dispersion. Okay, so no sidebands. But then, as this gyrotropic motion sets in, you see that more and more of these bands are populated in our system. And then we wanted to see, or the nice thing actually, and the coolest thing is, so in the simulation, we always drove actively this gyrotropic motion. But in the experiment that I already showed you before, we didn't even drive the gyroscopic motion. The system itself starts this process. So if you have only a high frequency drive of your magnon modes, you see that there is, for example, this one is now a different system just to be able with the BLS to measure the high frequency mode and the gyroscopic mode at the same time, which is a bit tricky in the Brilliant Light Scattering microscope. But anyway, we now drive at a little bit above 10 gigahertz, this mode up here, and look at it. What does it do with increasing driving power? And above a certain threshold, you see that the gyrotropic motion kicks in down here. And at the same time, we also have the frequency comp that kicks in. Meaning, we don't need to drive the gyrotropic motion by some external drive. The system itself, but via the nonlinear coupling, populates these Floquet magnon bands. And I think that's very cool. And if you now increase or look at this in time, temporal order, you see that the more power you put into your drive, the faster this nonlinear process kicks in. For example, at 14.5 dBm, you have a certain delay until you can actually measure your gyrotropic motion and the frequency comb. If you go up to higher powers, this delay is much smaller, simply because you reach the nonlinear threshold much faster. And then we wanted to play with this and see if we can somehow control it, for example, with the DC pulse. Okay, so this is a slightly different experiment. So we drive now this high frequency mode up here, this F and M, and also look at it in time response with the BLS. And we do not drive the gyroscopic motion at all. So there's no spontaneous self-induction of this Floquet bands. And there's also no drive of the gyroscopic motion by some RF that we feed in. It's just the high frequency excitation. And then at a certain point in time, we kick the system with a very short DC pulse, okay, just by using the same antenna. If we have a 2.5 nanosecond pulse, you see after the pulse, we get a very nice frequency comb with all these modes. And this persists as long as we have the drive of this high frequency mode. If we now make the DC pulse a little longer, 5.4 nanoseconds, do the same experiment, there is no frequency comp. You see maybe a little bit distortion here, but definitely no frequency comp. And why is that, we were wondering? Well, it's again related to the gyroscopic motion of your core. If you look at in simulation what's happening on the time scale of 2.5 nanosecond pulse, you kick the pulse. As long as the pulse is on, you shift your equilibrium position of the vortex core to the side. That means the core starts to gyrate, but then by the time the pulse already ends after 2.5 nanosecond, you're here with your core. And then the equilibrium position is back in the center, so the core just continues to gyrate around this new equilibrium position. And this, of course, leads to Floquet bands, because we have the periodic drive of the ground state. If we look at the 4.5 nanosecond pulse, we just match the period of one drive of the vortex core around its new equilibrium position. So by the time we switch off the DC pulse, the core is in its equilibrium position and it does not gyrate anymore. It's just frozen again in the center, meaning you have a static vortex, so no frequency comp, no Floquet bands at all in the system. If we do this for different pulses, see here we change the duration of the pulse length. Whenever we hit regions that are close to the period of one circulation, you see that there is no frequency comp generated. And that's simply because we nicely can control the position of the core and thereby nicely control the Floquet magnon bands. And to show you that it's really all about the core, or give you, let's say, one final proof, I hope, we did in another experiment where we took one of the samples that we had, 2-micron disk here, on a gold strip line antenna, and we have Gregor Lavacek at our institute who's operating a helium-ion microscope. And with the helium-ion microscope, you can very precisely drill holes into your material. And that's what he did. So he cut holes 100 nanometer in diameter, or this one 200 nanometer in diameter, so that we actually remove the center part of the disk. And with that, we remove the vortex core and do the same experiment. So this is the measurement on the disk. You see that there is the frequency comp. If we shoot out the vortex core on the sample with the hole, there's no frequency comp, simply because we cannot couple to the gyrotropic motion of our core and cannot populate any magnon Floquet bands in this system. And with that, I am actually at the end of my talk. There are a few things I hope you remember from our talk. So these nonlinear interactions in magnetic vortices can be used to actually do pattern recognition of temporal data streams of microwave signals. That the energy of a spin wave mode that you excite in a magnetic vortex can sustain and couple directly to the vortex gyration, and that by that we can change with a tiny object as the vortex core that's just precessing on a tiny orbit, change the entire magnon spectrum inside this, for example, also in the 5-micron disk, right? Only the tiny movement changes everything for the entire disk, which I think is actually quite cool. And then last but not least, for me, gyrotropic motion and high frequency magnon modes were always separate things and they didn't interact. But I was taught better, so now I know that actually the vortex gyration can be treated as any other excitation in your system in a magnon, and it does magnon-magnon scattering with all the other modes inside your vortex core, inside your magnetic vortex, so to say. And with that, I would like to thank you very much for your attention, and I'm happy to answer any questions that you might have.
Thank you very much for this interesting talk. We can thank the speaker using the reactions buttons. This talk is open for questions. If you have any questions, please raise your hand and I'll call your name. The first question, Alex Hamill, please go ahead and unmute and ask a question.
Hi, yeah, thank you for the talk. I thought that was really interesting. One thing I was curious about is, have you tried like applying an excitation at the gyration frequency instead of a DC pulse? So like
Yes.
coherently exciting at 94 megahertz or something?
Yes, yeah, we did that in different systems, different sizes of disks, and with different frequencies, also off resonance. So it's pretty easy to drive the gyroscopic motion off resonant. And then you see that the frequency comb and the Floquet bands, they change their spacing, right? Depending on the drive that you put in. So that's also something we did. I just didn't have time to cover it all, or I didn't have it here, sorry.
Oh,
But yeah,
of course, yeah. Okay, very interesting talk though. Thank you.
thank you.
Dr. Carl Patton, please go ahead and ask a question.
Hello, Carl.
Hi, boy, haven't seen you in a long time.
Yeah, haven't seen you. Good seeing you.
Well, this is an incredible talk and incredible work. I'm just sitting here remembering how much progress you guys have made in all of this.
Thank you very much, Carl.
And I just have a simple question.
Yeah.
So this is all permalloy?
Yes, it's all permalloy.
And what's the composition?
8119.
Okay.
So the standard, pretty much.
Yeah.
Yeah.
People say NIFE and you don't know what
Yeah.
they mean unless you ask. And
Yeah.
what is the thickness of the permalloy?
It's mostly in all studies 50 nanometer, 50.
Okay. 50 nanometers?
50, correct.
Okay. So in my old notation, it's 500 angstroms.
Correct.
Okay. That's about the right range for all of these different structures to happen. So I'm happy to see that. But I guess one question in the back of my mind, just from all of my work in the past, is a permalloy is not YIG, of course,
Yes.
and it's got a larger damping, or
Yeah.
whatever you want to call it, relaxation rate.
Yes.
So it's kind of interesting to me, and probably because I couldn't catch all the details, but so you can see all of these confluence and splitting 3 magnon effects in permalloy films with incredible, relatively large damping. So
yeah, that's the nice thing. We don't even need YIG.
yeah, that's great. Okay. So very nice work. I appreciate you presenting this today.
Thank you very much, Carl.
Hey, Dr. Laura, please.
Hi, Katrin. I don't know if you remember me.
Yeah,
the last
I do.
time I saw you right was in Inheritance Group 2009.
Yeah.
I'm really proud of the work you did, the progress you did over there. That's very interesting. So,
Thank you.
following Dr. Patton's question, so in terms of materials, do you think this phenomena will be observed in other, like, let's say, materials like coffee bean with the perpendicular magnetic anisotropy? Because it will be very interesting, I mean, to have like hybrid functional systems.
So I know it's in cobalt iron boron and cobalt iron. We tried it already and it works.
No.
But not with PMA.
Okay,
I
see.
If you have PMA, or for example, if you saturate your YIG or permalloy out of plane, of course the dispersion changes totally, right?
Okay. Mm-hmm.
So you don't have this distinction between backward volume and Damon-Eschbach character anymore, and the dispersion is all different.
But for in plane, do you see similar effects like in plane? I mean,
in plane, yes. If you have a vortex structure, it's at least the materials we studied so far, you always nicely reach this nonlinear regime, and you always nicely get this 3 magnon splitting and confluence processes.
Okay, very interesting. And then is there any thickness dependence? And I know you studied like one thickness here.
Yes. So the most of the work I showed you was on 50 nanometer. Actually, I wasn't quite right when I answered Carl, because we have one sample that was not 100 nanometer. And the main reason to make it thicker was for us to be able to push the gyrotropic motion higher. And then we were able to measure it with a BLS, because reaching the low frequency limit for for the Brilliant Light scattering is typically around 500 megahertz. You can push it a little bit and go a little bit lower, but it's difficult to measure the gyrotropic motion directly. And that's why we had the thicker to actually get it to higher frequencies.
Okay, thank you very much. Very nice work.
Thank you.
Fantastic. Do you have other question? By the way, if you are watching this on YouTube, you can also type the questions in the chat box. I can read it for you. Oh, Yaroslav, please go ahead and ask a question.
Thank you. The question is about this last part where you drilled the hole in the disk.
Mhm.
And I'm not just familiar with that, and you're saying it's obvious that there will be no gyrotropic motion because of the hole.
Yeah.
And so, like, if I try to pose this question as in the following manner, suppose I make the diameter of the hole, theoretically, smaller and smaller,
Yep.
and eventually it becomes equal to the core size of the vortex. Will it restore the vortex motion? Can you still have it?
Even in the 100 nanometer hole sample, we can restore the frequency comp. If we crank up the power even more, or if we, for example, apply a little bit of in-plane field and generate a vortex core that's just a little bit off-center, then we can get back the Floquet bands. And also, if we drive the system so hard that the radius of the gyroscopic motion is large enough so that it's actually, the core is then generated again, it's created, and then it actually gyrates around the hole in your system, and then you get again the Floquet bands.
So do you think that if you make a simulation where the core is actually inside the hole, but the outside is still a vertex, then somehow that kills the gyroscopic mode? Or
that strongly depends on your drive power. If you then only drive a little bit your system and you don't create a new vortex core, then you will not see a frequency comp. If you drive your system such that you already have a new core that's outside your hole, then you directly have a new frequency comp again.
And do you know if this is something that other people studied before you, or you actually did this hole for the first time?
I don't know. I actually, to be honest, I don't know. I did not come across work that tried that already, but I can't claim I did.
Yeah, sure. I mean, it's not a question about priority, but simply about knowledge, because it's interesting. Yeah. Okay. Thank you so much.
You're welcome.
Great. Do you have any other question? I just have one clarification question. For the experiment you did later for the Floquet band, was the drive with the strip line or with the omega antenna?
That's a good question, actually. So both is possible, which surprised us a little bit. If you have the omega antenna and you drive it very, very strongly, then we still get a frequency comp and still get Floquet bands because of this nonlinear coupling. So initially, we did not understand how with the homogeneous out-of-plane excitation would we ever drive and couple to the vortex core and have a gyrate, right? That was puzzling, at least to me in the beginning. But I think it's simply because we drive this spin wave mode so strongly that it has the nonlinear interaction with the core that drives this. Okay, and I think even, let me see, no, I just escaped this for a quite short time. I showed this quite a bit, right? This measurement here. I think what you see here, this broadening of your spectra, is also a frequency comp, which we in this case cannot resolve because it's a 5 micron size disk and the resonance frequency would be, I think, around 90 megahertz or something. So the resolution of our BLS is not good enough to resolve this. But I think all these broadenings here are also frequency combs in this case.
I see. It's very interesting. And when you say you have to drive it hard enough, can you translate to the magnitude of the micromagnetic field? Do you have estimation how big the field needs to be to peak into the nonlinear regime?
Yeah, that's a bit tricky. Unfortunately, we always give numbers in form of dBm output of our signal generator. So we're a bit lazy really estimating the field because there's so many unknowns in our system that it's difficult to really know what current arrives at our sample. But from the simulation, we can say that I think you need only a few millitesla to have the 3 magnon splitting regime. And with the gyro, I mean, to generate the Floquet bands, I can't 100% tell you right now, because we only did this experiment where we have the drive also. And if we drive the gyrotropic motion, sorry, then you get instantaneous response, right? There is no threshold in this case. It's only if you drive the high frequency mode and then rely on this nonlinear coupling that you need to cross a certain threshold. But for that, I don't have any numbers for the fields that you need. I'm sorry.
No, that's okay. Yeah, thank you. The 3 magnon threshold is already very useful. Great. Do we have any other question? If not, I guess we can stop the live streaming for now.